Morning, everyone. Thanks for coming to attend my talk, and thank you for the opportunity to speak. I hope everyone can hear me okay. So I'm going to tell you about some computational work that's being done in my group at the University of Michigan. In particular, I'm going to focus on, let's see, the right button, solid electrolytes. We're going to focus on some of the issues related to developing a viable solid electrolyte. And before I go any further, I want to acknowledge one of my graduate students, Young-Ho Yu, who is basically responsible for all of the calculations I'll present today. But we also have some experimental collaborators, and I'll try to convey some of their data as appropriate as we go through the talk. And so at U of M, we have Jeff Sakamoto and Neil Dasgupta's group. Eric Herbert at Michigan Tech has been doing some mechanical properties testing. At the Army Research Lab, there's Jeff Wolfenstein and Jan Allen, and also at Oak Ridge, there's Jagjit Nanda and Nancy Dudney. So as I mentioned, this talk is going to be about solid electrolytes, and so this is an exciting time for solid electrolytes in batteries, because after, I don't know, maybe 40 years of searching, within the past 5 years or so, a handful of solid electrolytes that have high ionic conductivity have suddenly appeared. I don't honestly know what's changed in the past 5 years as to why we've had some success in discovering these compounds, but suffice it to say they're here, and that's really good news. But what we're starting to uncover is there are many other challenges beyond just having high ionic conductivity, and that's going to be the basis of my talk today. So what does a solid electrolyte buy us? Well, it basically buys us two things. It buys us increased capacity and enhanced safety. And so if we were to look at a normal lithium-ion battery, so I'll use this cartoon here to the left. A normal lithium-ion battery has a transition metal oxide, an intercalation host as the cathode. On the negative side, or the anode, we would have intercalated graphite. And in between, we'd have a liquid electrolyte. And so what our hope is that we'd be able to replace that liquid with something that's a solid. So in here I'm mentioning LLZO as a specific example of a solid electrolyte. In fact, this is the composition I'll spend basically all of my time talking about today. I'll tell you more about the details of LLZO in a moment. But the way we get to higher capacity in these batteries would be instead of having that intercalated graphite on the negative side, the graphite of course takes up space, costs us some volume, costs us some mass. Instead, let's remove the carbon and just have a metallic lithium anode. So for example, a metal foil of lithium. That would increase the anode capacity by about a factor of 10 theoretically. So the reason we don't do that today is because of the so-called dendrite problem, which I mentioned here. So if this again were a liquid and up against lithium metal, when we cycle that battery, the deposition and stripping of lithium ends up being non-uniform, and we developed protrusions that can cross the separator and form a short circuit between the negative and positive. So this leads to a very bad, you could say an explosive situation in a lithium metal battery. The conventional wisdom, however, is if we have a solid electrolyte, something that's very stiff, we can press that up against the lithium metal and prevent those lithium dendrites from growing. So we'll talk about the prospects of achieving that in a moment. So in addition to having a lithium metal anode, and that can of course just be coupled with an existing intercalation cathode, and that would give us a battery everyone would like to have. That's probably the closest to being achievable. This lithium metal anode opens up other advanced chemistries such as lithium sulfur, lithium air. Here's some example of some lithium sulfur cells which could be constructed. Thinking about safety on the other side here, one thing you may know about these liquid electrolytes, in addition to the fact that they don't really help us with the dendrite problem, they're also flammable and volatile. So if we can get rid of those liquids, replace them with a solid, we have an immediate increase in battery safety. In fact, one could imagine an all-solid state battery where instead of using even lithium metal here, we had another intercalation host as an anode, LLZO or some other solid between them, and then of course another intercalation host is the cathode. So this would be a totally dry system, again, improving safety. So those are two really good reasons to focus on solid electrolytes. And like I mentioned earlier, we have now a handful of compounds that have apparently the requisite ionic conductivity to be a viable electrolyte. As I'll show you, there are some other challenges which we need to address, and the vehicle I'll use for illustrating those challenges is this compound LLZO, which has the composition you see here. So this guy has a conductivity about half a millisiemens. This is approaching what we would have for a conventional liquid electrolyte, which would be about 1 millisiemens. I'm showing on the left the cubic unit cell. LLZO can in fact adopt two different polymorphs. There's a tetragonal and a cubic phase. It's the cubic phase which we're most interested in because this is the one that gives us the highest ionic conductivity. And as you can see, it's a complicated system, about 192 atoms in that unit cell. And so for someone who does quantum mechanical calculations, 192 atoms is a challenge, just based on the quantity of electrons there. So the reason this material works well is illustrated, at least as an ionic conductor, is shown here on the right. And what I'm illustrating in this case is just the lithium sublattice. So lithium here is this light shade of blue, and as you can see, it's comprised of these interconnected rings. So these form an isotropic structure, and the lithium sites are about half occupied. So there's a lot of vacancies for lithium to hop into, which again also is responsible for the relatively high conductivity. So in addition to LLZO, I also mentioned there are some other compounds. It turns out there is no one particular category of crystal structure that makes for a good solid electrolyte. There are amorphous phases, glass ceramics, various other things out there. And so we're trying to understand fundamentals about what makes for a good solid electrolyte also. So in addition to, well, despite having those high ionic conductivities, many other challenges are starting to pop up as being, I guess you could say, roadblocks for making a solid electrolyte-based battery. And I'm going to talk hopefully about 4 of them. These are, again, all focused on LLZO. And these are issues which have come up either from experiments or from some of our calculations. And so you can think of the organization of the talk as being 4 mini talks focused on these 4 separate things. Starting with mechanical properties, I'm going to focus on experiments and calculations that measure the elastic properties of LLZO. And remember, our hope here is that by putting a stiff solid electrolyte between the electrodes, we can prevent the formation of these dendrites, which you see here in red. So let's start with that. So starting there, I want to go back to a model proposed by Monroe and Newman. So maybe about, let's see, 12 years ago, Chuck Monroe and John Newman started to think about what properties would be needed for a viable solid electrolyte. And at that time, they were mostly focused on polymers, which can be rather soft. And they developed a finite element model, which you can see here, based on linear elasticity. And what they concluded from that model was that the dendrites can be suppressed if we have a solid separator which is sufficiently stiff, and that is quantified by looking at the shear modulus of the solid electrolyte. Their model suggested that if you had a solid electrolyte that had a shear modulus G, which is twice that of lithium metal, then you had some hope of suppressing dendrites. So we set out to measure the shear modulus and basically all the elastic properties of LLZO in hopes of comparing with the elastic properties of lithium to see if LLZO could satisfy this criterion. And so this is a combination of first principles calculations, which I'll of course tell you the details of in a moment, but also some experimental work using acoustic impulse excitation and nano indentation experiments done by some of our experimental collaborators. So here's the systems we're going to focus on. So these are LLZO with some dopants, either of aluminum or tantalum. So these are alliovalent dopants, which basically create more vacancies on the lithium sublattice. So again, possibly resulting in higher conductivity of lithium. In fact, that's what happens. These are generally agreed to be 2 of the highest conductivity compositions. So these are what we've used in our calculations and in the measurements. And so a calculation using density functional theory, which is a quantum mechanical method, was performed to evaluate all of the elastic constants of LLZO. And so this is a cubic material, so we have 3 elastic constants we care about: C11, C12, and C44. And by evaluating these, we can combine them in different ways using these averaging schemes to get, for example, the polycrystalline isotropic shear moduli, which is the main thing we want to get out of this calculation and compare with that of lithium, but also Young's modulus, the Poisson's ratio, and these moduli can also be resolved into different crystallographic directions. And the way this works is that we basically develop a strain tensor or some method for straining the crystal, and this is shown here on the right with a cartoon. So if I had a cubic system, I could, for example, apply a uniaxial strain of different degrees of magnitude, and then I fit the total energy of that strain. I fit the total energy versus strain. In this case, it's a volume strain or a uniaxial strain to a polynomial, and the coefficient of the quadratic term is related to the elastic constant. So you can see there's different curves here. These represent different convergence criteria. Basically, we increase the precision of the calculation until we see convergence in these energies. So with this data, we have basically enough now to report our calculation results, but let me take a step back and show you some of the experimental data and why it's related or can be compared to our calculations. So our calculations are done on a single crystal, there's no defects, and a real material, of course, doesn't have those properties. But what our experimental collaborators are able to do is make very phase pure LLZO with very low porosity and with rather large crystallite grains. So you can see here on the right, this is some SEM fractography for a sample that was almost 99% of the theoretical density, so very, very low porosity. Also little evidence of second phases present in this compound. So Eric Herbert at Michigan Tech took one of these samples and did some nanoindentation. In this case, looking at both of those compositions, and so what's plotted here is the Young modulus as a function of displacement of the nanoindenter into the surface. And as you can see, once you get beyond a surface region, both of these compositions have roughly the same value of about 150 gigapascals. And so comparing, so this is a table that summarizes the comparison between the experiments and theory. So we have the aluminum doped case, the tantalum doped case, and what I want to focus on is just the shear modulus, G. So from the calculations, we're getting about 61 or 60 gigapascals, and that compares very well with the experiments. In fact, we have the impulse excitation, the nanoindentation giving us values around 58 to 60. An earlier study using ultrasound measurements gave a value of about 60. So this is really good agreement between theory and experiment. This is also a relatively high shear modulus, which gives us some confidence that, at least according to the Monroe-Newman model, we'd have some hope of suppressing dendrites. And of course, we want to compare with the lithium value. So we also reevaluated BCC lithium. And so this is our calculated value of about 4.25 GPa for the shear modulus. That agrees rather well with some older experimental measurements. So as you can see, we are well above this factor of 2 threshold to satisfy the Monroe-Newman criterion. So for lithium, we reported a value of 4.25. So 8.5 should be sufficient to suppress dendrites. And for LLZO, we're getting values of around 60. That's about 10 times the shear modulus of lithium. So in principle, we should be able to check the box. Monroe-Newman says that this is a stiff enough solid to suppress dendrites. We should, however, be careful. Not every solid will have, say, the low porosity that we've seen in this particular sample, and assembling that solid electrolyte into a cell and maintaining, say, low porosity at the electrode-electrolyte interface is something that may not be easy to do. So even though we have a bulk system that looks like it's suitable, putting that material into practice could cause some problems or raise some issues. So I like to say that high stiffness is a necessary but not sufficient condition for a viable solid electrolyte. In fact, that's the whole point of the talk, that there are some other issues that we also need to address beyond just this dendrite suppression. So mechanical properties look good for LLZO, and you might have said, well, that probably is unexpected. Most oxides have a high shear modulus anyhow, or relatively stiff. It turns out there are other solid electrolytes, for example, LGPS, that don't satisfy the Monroe-Newman criterion. They're actually good ionic conductors that are relatively soft. So one needs to be careful. And we've also seen some surprises, even with satisfying the Monroe-Newman criterion. Jeff Sakamoto's group has recently reported that when you take an LLZO pellet and you cycle it in a lithium LLZO lithium symmetric cell at I'd say a modest current density, bad things happen. And so what happens is that during cycling, it appears as though a short circuit has formed. And taking the cell apart, looking at the LLZO membrane, what is seen are these black linear features, which would be on both faces of the pellet. And if you crack the pellet and get lucky enough, the fracture surface will intersect this black region. And that's what's magnified here to the right in SEM. So if you look at this ribbon right here, this is basically one of the black ribbons uncovered by the fracture surface. And then zooming in with SEM, you see this web-like structure. So these are, in fact, based on Auger analysis, these outlines are, in fact, a lithium metal. And the outline you see is a characteristic shape of a grain. So in this case, the grain diameter is on the order of 2 or 3 microns. So even at relatively low, I'd say, or gentle current densities, this solid is not able to suppress dendrites. And dendrites, I think, here should be used in quotation marks because these are of course, not dendritic microstructures. But we are seeing lithium metal penetrate along the grain boundary network. And this is something that, I guess, based on a strict interpretation of the Monroe-Newman model, we would not expect this to occur. But of course, the Monroe-Newman model knows nothing about microstructure, so we shouldn't be too harsh. But the message being here that microstructural properties are also probably very important in solid electrolytes that are polycrystalline materials, but so far haven't received much attention. So that brings me to the second part of the talk, where as a segue into looking at what effect grain boundaries have on the performance of LLZO, we've started out by looking at transport along those grain boundaries. So before we get into this, I think it's important to have some history about how grain boundaries affect ionic transport in other oxides or other solids. And basically, you can have any possibility here. So for things like aluminum, hafnium oxide, uranium oxide, ionic diffusion is enhanced by grain boundaries, but in other compounds, grain boundaries slow ion transport. In the case of LLZO, there hasn't been a ton of study so far about what effect grain boundaries have. What little has been out there seems to suggest that it's not a deal breaker, but grain boundaries do have some effect at slowing ionic transport. So for example, in samples that were hot pressed at 1,000 degrees C, the grain boundary contribution is about 26%, or about a quarter of the total LLZO resistance. And of course, changing the processing conditions, for example, heating to higher temperatures, increasing the density by pressing more, those would increase the grain size, reduce porosity, and those in principle could be brought to bear to improve this grain boundary resistance. I guess it's a matter of how expensive and how complicated are these processing techniques if you want to do it on large scale. So what we would like to do is to look at what's happening at these grain boundaries and understand the transport there using Monte Carlo and molecular dynamics. So this is different from the density functional theory calculations I mentioned earlier, which were basically a quantum mechanical technique. These are classical simulations. We have a prescribed interatomic potential. And we go classical in this case because these are very large simulation cells on the order of, say, 2,000 to 15,000 atoms necessary to get a grain boundary-like region and a bulk-like region in the same simulation cell. So one problem is that even though, well, bulk transport in LLZO has been widely studied, as I mentioned, not much has been done for grain boundaries. A complication, or maybe a reason that few studies exist, is that we don't really know much about the structure of grain boundaries at this point from experiments. And so what we have done is use some model systems that are based on grain boundaries which are known to have very low energies. And here I'm referring to some work based on BCC iron. And so what's plotted here is the grain boundary energy as a function of misorientation angle between two crystallites that are brought together to form a grain boundary. So this is some work from Mark Horstmeyer's group. And what you'll notice is that the grain boundary energy, of course, by changing this misorientation angle, there are certain misorientations where we have these notches in the boundary energy. So these are special boundaries that have very low energy, and in thermodynamic equilibrium, we would expect them to have some population of the grain boundary network. But of course, we would still like to know what are the realistic grain boundaries, and hopefully someone will provide us with the 5 degrees of information necessary to get those structures and use them in our models. So the reason we use iron is that the zirconium sublattice in LLZO is also body-centered cubic. And so here I'm just illustrating the zirconium sites. And so here are the grain boundaries. So there's a boundary, 3 different grain boundaries we've picked up. There's a boundary in the center of the cell and a boundary on the periodic edges. And here's some models with all of the atoms drawn in. So the question we would like to know is what is the composition in the grain boundary plane? Is it stoichiometric LLZO, or is it something else? And how does lithium move along those grain boundaries? And so the way we do that is to follow a series of computational steps. We start off with the as-built structures you saw on the last slide. We relax the forces on those systems first. That's all done at 0 Kelvin, and then we heat to a high temperature. So here we're roughly mimicking some of the processing conditions with molecular dynamics. We equilibrate for another 3 nanoseconds at the target temperature. Then we switch over to Monte Carlo. So here we're exchanging atoms to allow for rapid evaluation of the composition at the grain boundary plane. And then finally, we take those structures, those equilibrated structures from Monte Carlo, put them back into molecular dynamics, and ultimately get out the diffusion coefficient, which is based on the mean square displacement, the average mean square displacement of all of the lithium ions in the cell. And so for this, we're using a so-called Morse-type soft BV interatomic potential, which is from Stefan Adams' group in Singapore. So this has already been used a few times to look at LLZO. So the first thing we want to know is, well, how does the composition of the grain boundary compare to the bulk composition? And so what we do is we take a planar average of, say, the lithium concentration, the oxygen concentration, or the lanthanum and zirconium concentration as a function of position in the cell. And remember, there's a grain boundary in the middle, there's one on the edges. And so if we look just at the lithium at the top, for these three different boundaries, we see there's a peak in lithium concentration in the boundary plane. So there's some enrichment of lithium occurring here, which also coincides with a somewhat weaker enrichment of oxygen. So perhaps there's some electroneutrality constraint here that we can't overload the grain boundary with positive lithium, but there has to be some anion present to balance that charge. But then for lanthanum, zirconium, there's really not much of a change in composition as we go across the cell. So maybe this grain boundary is enriched in, for example, lithium oxide. What we do then is we take that structure and we run molecular dynamics on it to estimate the diffusivity. And in this case, we're going to focus specifically on what happens in the grain boundary region. So I don't know if you guys can see from where you're sitting, but there's a little red box that's focused on the grain boundary region in each of these cells, and then there's a black box, which is meant to isolate the bulk-like behavior. So one way we can qualitatively assess how rapidly lithium is diffusing is to plot the trajectory of lithium. So in this case, we use a 5 nanosecond MD window, and for each one of those steps, we plot a spot of blue to represent each lithium atom's position. And so, well, you can see at the top here that the blue basically fills the volume of the cell when we look along the tilt axis. But if now instead we look sideways, so in these two bottom rows, I'm looking, well, if I were up on the top, I'd be looking to the right or looking horizontally. So looking, so perpendicular to the tilt axis in these two rows. Let's first look at the bulk. So looking at the bulk region, we see a trajectory which is relatively well connected. Lithium can percolate and move rather freely through the bulk region. But then comparing that to what's happening in the grain boundary, you'll see that these trajectories are now more fragmented. There's basically gaps between the lithium locations, which is indicative of a slowed or disrupted diffusion in the grain boundary plane. So again, this is a qualitative picture shows us what we expect, or roughly speaking, what's happening with respect to mobility in the grain boundary region. We can also look at this using an equivalent technique where we just highlight the lithiums which are moving less than a certain mean square displacement. And here we've picked a value of less than 4 angstroms squared in any half a nanosecond interval. This is roughly about 15th or 20th percentile of the displacements of all of the lithium in the cell. And what you can see is, so those atoms which are limited in their mobility, I've colored here in red, and those are all concentrated on the grain boundary region. And so this is a plot of basically the same thing, the fraction of immobile lithium as a function of position at different temperatures. And so you see these peaks here indicating a higher concentration of things being immobile in the boundary plane. So based on these qualitative pictures, we already expect there to be some degradation in lithium ion mobility in the grain boundary region. And of course, we can evaluate now the diffusivity as a function of position. And so this is the total diffusivity of the 3 different grain boundaries. Again, remember the grain boundary planes are here on the edges, and there's also one in the middle. And at 1,000 Kelvin, there is obviously a difference, a reduction in the grain boundary diffusivity, but it's not a huge effect. This is only about a factor of 3. So that's not a huge penalty, at least at this temperature. We can also look at for anisotropy by projecting these diffusivities. I don't know if you can see these colors, but the different colors represent diffusion in either of the 3 Cartesian axes. And so an anisotropic grain boundary would have a big spread in the diffusivities in the boundary plane, and we don't really see much of that effect here, which suggests that at least for these boundaries, there's limited anisotropy for diffusion. We can also make Arrhenius plots to estimate the activation energy for diffusion. And so what we found, and highlighted here in yellow, these are the activation energies in the grain boundary region for those 3 grain boundaries, and this is the comparable value in bulk. And so you can see for 2 of the 3, we've got an increased activation energy, again, consistent with slower diffusion. One of the activation energies is roughly comparable to bulk. So basically what we're seeing here in this case, again, at least for these model grain boundaries, is that we are seeing something consistent with the experimental data, that is slower transport along the grain boundaries as predicted by these calculations. We also can get information about the composition. So some enrichment of lithium and oxygen was observed. What lithium is immobile is largely focused on the grain boundary planes. And that grain boundary diffusion appears to be isotropic. So if we can extrapolate, you may say, well, what's happening at room temperature? So of course, we've only looked at high temperature in these particular calculations, but if we were to extrapolate these out to room temperature, I would expect that there would be a much bigger difference or a bigger penalty associated with grain boundary diffusion at those low temperatures. So what we're thinking about now is, well, here's a realistic and quite ugly grain boundary that we've got from Oak Ridge. This is something in principle we could run a calculation on. In fact, we've mapped the atom positions and built an atomic scale model. It's not a pretty system to calculate. But probably more interesting is to look at the nucleation of lithium metal, and this comes back to those dendrites penetrating the grain boundaries, to understand what is the thermodynamic driving force and the mobility of rather than lithium plus, lithium metal, as we form these dendrites. Okay, so I think we're about 25 minutes into the talk, so I think we're doing well. Let me switch now to the third little nugget of information focusing on the electrochemical window of LLZO. And before we get there, let me remind you about stability of electrolytes in general. So here's a diagram which maybe some of you have seen in one of John Goodenough's review articles from Chemistry of Materials, where as a function of energy, he plots the electrochemical potential of the negative electrode and the positive electrode. Of course, the difference between those would be the open circuit voltage of the cell. And the point of the diagram is to illustrate how the LUMO or HOMO, if we were dealing with liquid electrolytes, how those influence stability of the electrolyte. And so for stability, what we would like to see, for thermodynamic stability, is that the LUMO, this unoccupied level, should be higher than the electrochemical potential of the negative electrode. In many lithium-ion conventional liquid electrolytes, for example, the LUMO of the solvent is actually below the mu A of the anode. That results in reduction of the electrolyte, and chemical fragments form. This is the process which leads up to SEI formation. So in that case, even though in, say, a liquid electrolyte for lithium-ion batteries, this LUMO tends to be reduced, the products that result from that reaction kinetically stabilize the electrolyte such that this level effectively moves up, and that SEI formation at some point stops. On the other hand, the HOMO, what we worry about there is oxidation of the HOMO by the cathode. Of course, similar considerations occur there. We'd like to have the HOMO below mu C. So this is all for a liquid phase. We'd like to translate this information to look at the stability of a solid electrolyte. And I should say that in liquid systems, it's now rather routine to estimate the positions of the HOMO and LUMO and assess whether a given component of your electrolyte is suitable for use in a battery of a given operating voltage. Not much has been done in solids to get this same sort of information. We can get things like the band gap, which would be here Eg, between the conduction band minimum and the valence band maximum, but it would also be really helpful to know the absolute positions of these band edges. So where does this blue line fall, for example, with respect to these potentials, which we get, as I'll show you, by going through an analysis of using the vacuum level. So we've done this sort of analysis. I think I've already said all of this. Basically, for LLZO, we're at the early stages of understanding its properties. And when we wrote this paper, good estimates of, say, the band gap and the band edges did not yet exist. And so this is important to understand, again, the stability of these materials when we put them into electrochemical cells against electrodes, which could oxidize or reduce them. So we've done some work along these lines already looking at magnesium batteries, and so this is a bit of a diversion. But to show you what some of our capabilities are, here are 4 common solvents which are used in magnesium-ion batteries. Using GW calculations, we were able to predict, say, the HOMO and LUMO levels of the isolated molecule. Again, that's something which can be routinely done with quantum chemical techniques. Our contribution has been to take those levels and ask how do they change when you take one of these molecules and put it at an interface with an electrode. And that is shown for these 2 columns over here. So for example, if I take acetonitrile as an isolated molecule, it has a huge band gap or HOMO-LUMO gap of about 11 volts, or 11 eV in this case. When I take that molecule and put it on a magnesium surface, the LUMO shifts down by about 1.6 volts. So this indicates what we call, this is renormalization of the HOMO-LUMO levels due to interfacial interactions. And so this is something which is, I'd say, an important consideration that one would look into after first screening for molecules that are appropriate in their isolated environment. Something similar can be examined with respect to the HOMO by looking at interactions with a model cathode material. In this case, we just use magnesium oxide. And so the upshot is that you can see that the isolated materials have rather large gaps, but in some cases they shrink by up to, say, a quarter of their total size due to these renormalizations at interfaces with electrodes. So we would love to do this with solids. We can't yet include these interfacial effects. And so what we're doing right now is looking at the isolated limit of solids and again trying to position those HOMO and LUMO levels, or CBM and VBM, in an absolute sense. So the first thing we did was look at the band gap. Here's an example of the calculated band gap of LLZO as a function of theory. And at the top here we have some ground state methods which we know will underpredict the band gap. But looking at some quasi-particle methods based on the GW technique, we get this is probably a rather reliable estimate of the band gap, about 6.4 eV. So that's our best calculated estimate. And I'd say that agrees rather well with an absorption measurement done on a transparent sample of LLZO. Ideally, we'd like to compare the calculations to photoemission data. Absorption data can underestimate the band gap a little bit due to, for example, excitonic effects. But even with that, we're doing quite well. So it would seem LLZO has a nice wide band gap, which would enable, in principle, the use of LLZO in a material, in a battery that would have a high voltage battery. So there's a few steps. In the interest of time, I'm not going to go through all the steps that we use to position these band edges. I'm going to summarize the results here on the right. What we do is we've built 2 slabs of LLZO, looking for low energy surfaces. And based on the electrostatic potential of that slab, so if you follow the black line here, this is the average electrostatic potential as a function of position across that cell, we can get an estimate of the vacuum level. And then by doing an equivalent calculation on bulk LLZO, this is the red line, we can align those electrostatic potentials, and in so doing also align the band edge position. So it's basically aligning electrostatic potentials, which are relative to the vacuum level, and there's a second reference there to what's happening in the bulk with respect to these band edges. And I can tell you more later if you like, but basically the upshot is that what we find is that in particular we should focus on what's happening up here with respect to the conduction band minimum, because these calculations are focused on equilibrium with lithium, so equilibrium with the negative electrode. What we find is that for LLZO, it looks like the conduction band maximum is actually slightly above the lithium-lithium plus level. So that's really good news. It's not way above the lithium-lithium plus level, suggestive of some moderate reductive stability. But this is quite different from what we would see, say, for most liquid electrolytes, where the LUMO would be below this level. So this indicates some perhaps enhanced stability with respect to reduction of LLZO. Some other experiments were done to look at the electronic transport through LLZO. I'm just going to cut to the chase here and say that LLZO is an excellent electronic insulator. More than 4/9 of the current is due to ionic transport. So again, another data point in favor of it being a promising solid electrolyte. So to summarize this portion of the talk, so here we are interested in calculating the electrochemical window. What we've looked at is the band gap of LLZO. We think that it's a nice wide band gap material. It's also an excellent electronic insulator. And the CBM looks to lie slightly above the lithium plus level. So we'd like to extend this Echem window idea to other solid electrolytes to see how others perform with respect to stability of, say, a lithium metal anode. Okay, so in the last 2 minutes of my time, let me tell you about some very new work which is not yet published, focused on low resistance interfaces. So I think it was Linda who used the word Oreo cookie before to describe these lithium solid electrolyte lithium sandwiches. And what we're interested here is trying to put these cells together in a way where the resistance between the lithium and the LLZO is rather low. Ideally, we'd like it to be as low as it could be in a liquid electrolyte. And so we're focused on this value you see right here. This is really small. But basically, this says the resistance of the lithium LLZO interface, and there's 2 of them in this cell. So the reason this could be a problem is because of some surface reactivity associated with LLZO. So, here's an example of some Nyquist plots for, again, that symmetric cell assembled without the LLZO coming into significant contact with air. In that case, we have, looking at the tail here to the right, the component of the resistance due to this interface is rather small. But if you let this LLZO system sit for 10 days under air, in fact, you can't even see these other 2 resistances. Basically, this interfacial resistance blows up and is huge. And what we think is happening here, we've done some calculations of the thermodynamics of this process, is we think you start with LLZO, and when it sees some water vapor, it reacts exothermically to form lithium hydroxide, and also some of the hydrogen from the water goes into the LLZO. It displaces some of the lithium and protonates the LLZO. A second step is that if there's some CO2 in the atmosphere, that will then react with the hydroxide to form lithium carbonate. That's also an exothermic step. And so this formation of this skin of carbonate and hydroxide is hypothesized to be the reason why this large interfacial resistance exists. And so people have, of course, already noticed this. For example, Eric Waxman's group has developed techniques for coating the LLZO with atomic layer deposition to try and minimize this reactivity with air. But what I'll tell you about is that you don't actually need a coating. One can just clean the surface of LLZO, get a much stronger interaction between the lithium and the LLZO, and basically all of the interfacial resistance goes away. So this is some work done also in collaboration with Neil Dasgupta and Jeff Sakamoto. And so this is some XPS showing basically the amount of either hydroxide, which is green, the orange, which is carbonate, and the blue, which is the oxide. The oxide is what is the proxy for LLZO. So we'd like to see this blue region be as big as possible and the area of the orange and green be as small as possible. And what one of Jeff's students, Asma, has done is looked at different polishing strategies, either dry polishing or wet polishing. So the wet polishing use a glycol-based diamond paste. And then after those polishing steps, they can also optionally heat treat the sample. And so what they found the best procedure is to go through this wet polishing technique and then heat the system up to about 400 to 500 degrees C. And in that case, most but not all of the hydroxide and carbonate disappear. And when that happens, there's a dramatic change in the wettability. So what I'm showing here are some pictures, some photographs of molten lithium metal on substrates of either lithium carbonate. This is dry polished LLZO, this is wet polished LLZO, and then this is wet polished plus heat treatment. And as you can see, for these 3 cases, there's basically very little interaction. So a large contact angle like this indicates very weak adhesion between the lithium metal and the substrate. However, when you wet polish and heat treat, this interaction becomes much stronger. This is something we can also calculate incidentally. So by building some models of the lithium carbonate or lithium LLZO interfaces, we can calculate the work of adhesion, and then through something called the Young-Dupre equation, we can back out a theoretical wetting angle. So you can see we're doing really well with the carbonate wetting angle, about 140, very similar to these 3. And we predict actually a stronger interaction between pristine LLZO and metallic lithium giving a 62-degree contact angle, actually stronger than what's seen here experimentally, and that's probably because even in this system there's still some amount of schmutz on the surface. So we can increase the wetting angle, we can reduce the amount of these surface contaminants, and the effect is that the interfacial resistance goes way down and the critical current density goes way up. So here's an example of that interfacial resistance as a function of heat treatment temperature with a zoom in at the higher temperatures. I've drawn a line here to represent a nominal value for a liquid electrolyte. So here you can see the interfacial resistance actually below that of a liquid electrolyte. And that also raises the critical current density. So here's some earlier studies. The critical current density is the current density at which dendrites are observed to first form. And so in this case, that current density is around 0.3 milliamps per square centimeter. And this thing cycles for at least 100 cycles without much change to the impedance spectra. So these properties seem to be maintained over some decent period of time. So this is my last summary slide. And so the notion here is that it is possible to make very nice interfaces between LLZO and lithium metal with rather low resistance following the experimentalists call this a straightforward cleaning procedure without the need for coatings. And this correlates with lithium wettability and was also assessed using the electrochemical phenomena or the impedance spectra that we also discussed. That's all. So let me stop here. Let me point my laser at Seung Ho. Again, he's the guy who's done basically all of the calculations I told you about. He's a very productive student. But here's some of the other members of the group. Most of the work I've told you about is funded by the US Department of Energy, the Battery Materials Research Program, a little bit from J. Caesar with respect to the magnesium ion work. And I think I'll stop here, and hopefully you guys have some questions. Thanks for your attention.
Thank you, John.
Yeah.
Fascinating variety of calculations. All done by one student?
Yeah. He's great. Yeah.
Okay, good. Questions for Don?
That was really nice talk, Don. I really enjoyed that. I was a little puzzled by the activation energy.
Yeah.
That you showed for the LLZO. This is the calculations at 1,000 degrees.
Yeah.
You have a value of 0.53 electron
Yeah.
volts. And
Does that seem high to you?
well, it does, based on the conductivity of 10 to the minus 4.
It is. It is a bit.
What is the,
It is a bit high.
so what's the calculated value?
Well, this.
Experimental value.
Well, it depends upon who's measuring it, but I'd say around 0.3, 0.35. There's values actually all of them out from about 0.2 to midpoint.
Yeah,
Yeah.
I saw numbers around 0.25.
Yeah. So this particular interatomic potential tends to underestimate the ionic conductivity of lithium. So that's why you see this value, which looks high to you. So here I'd say it's just most justified to compare bulk relative to grain boundary and not read into, say, the absolute conductivity. Yeah.
The fusion coefficients then would be really, really low.
Yeah,
and again,
yeah,
it would be
yeah,
in
yeah.
concert with
Yeah.
experiments.
This is sort of a typical failing of an interatomic potential. You can simulate big systems, but you maybe lose some accuracy. The other way we could do this calculation would be with density functional theory and ab initio molecular dynamics. But in that case, you might get, say, a few picoseconds of MD time, and the statistics associated with the mean square displacement would become very poor. So here we get very nice linear mean square displacement plots, but with some trade-off perhaps in the accuracy of the activation energy.
So the fact that the lithium is immobile, or fairly mobile in the grain boundary is, I guess, predicted by calculation. In reality, is this because maybe it is sort of something like Li2O in there?
It could be. I mean, we honestly don't know. We don't know at this stage. I mean, very little is known about what's happening in these grain boundaries other than, people have made some Nyquist plots and tried to back out what is the grain boundary contribution to the resistance. But chemical accuracy or, a nanoscopic probe of what is the composition in the grain boundary region I have not seen published at this point.
I'm sure there's other questions. I'll just ask one and then come back later. The measurement when you were looking at the electrostatic potential is
Yep.
on the slides.
Yeah.
Out of curiosity, did you take a particular surface or was that sort of a generic?
Yeah, so one of the issues which was swept under the rug here, we looked at many different surfaces. In fact, there's about 12 with different terminations. That's one of the reasons why we have, and so there's an... Yeah. Well, this is published, so you can, we can discuss the details, but the slab calculation is done on the two lowest energy surfaces that we found, say within the 100 direction and 110 direction, assuming equilibrium with lithium metal. So there's 10 others that we found were not competitive and therefore presumably not realistic. And so we use the lowest energy models to get this average electrostatic potential. You would get a different answer. So this is kind of like a it's kind of like a work function calculation where the dipole of the surface will affect the work function. So our logic here is to use the lowest energy surfaces. We presume those are the most realistic and would give the best estimate of the electrostatic behavior.
But it is quite facet. It is quite surface dependent. I mean,
it will be surface dependent, but honestly, we haven't. This is such an expensive calculation that we haven't done it for the other surfaces just to see how things change. If you go through, for example, there's hundreds of papers on metal work functions, which are easy to calculate. You could see, say, a surface dependence of the HKL index on the work function for those different systems. That would at least verify the general notion I think you're getting at.
So did you find a surface that was actually not so high, but was relatively lower?
Did I find a surface that was not so...
12 surfaces.
Oh yeah, well the two that I show here are the lowest of those 12. Yeah.
Just out of curiosity,
Yep.
the higher energy ones
Yep.
are where?
In terms of surface energy or in terms of these?
In terms of those.
I don't remember off the top of my head, but I have the data and I can show it with you. I think these were, as I recall, at least one of these was a clear winner where its surface energy was much lower than any of the other compositions we considered. I don't know if that's true for both of these. There might be another competitive surface for one of these.
So I mean, just sort of by extension, I guess
Yep.
if it's a higher surface energy
Yep.
on that surface, it would probably be more reactive and perhaps, I mean, that's not necessarily the case.
That's the general rule, yeah. That's my chemical understanding. Higher surface energy means more reactive. Like I mentioned earlier, what we would really like to do is fold in these interface effects. We're trying to do that. We can't do that with LLZO because it's just too big of a system. We're trying to do it with LOC, anti-perovskites, very nice small unit cell. So we'll see how that turns out. But so this is just based on finding low energy slabs, no interfaces at all. Yeah.
So your Yannick has sprayed lithium atoms on a variety of different materials.
Yeah. Okay.
And literally just like a gas phase thing. I'm pretty sure that if I recall correctly, that LLZO is actually stable to that.
Yeah, there's been some other, that Garrett's group and other of his descendants have looked at this chemically, where they compare the phase stability at lithium, at the lithium plus potential. This is a little bit different because we're focused on these energy levels. This is really, I'd say, electrochemical, but they're both important calculations. This one just happens to be a lot harder to do because of the level of theory that's needed. But I'd say that is what I've seen of their work and what this is showing us, that the conclusion is basically the same, some reasonable stability either electrochemically or chemically at the negative electrode.
So for the grain boundaries,
Yes.
you're assuming no change in concentration, stoichiometry?
We're assuming that the whole cell remains at the stoichiometric LLZO composition. We haven't done an open system calculation where, for example, we could increase the amount make the system oxygen rich or oxygen poor. That could be something which is done, but is not something we've done at this stage.
I'm also thinking you might get rearrangement.
Well, so the calculations here do allow for atomic relaxation. It's kind of hard to see based on the small images I showed you. I don't know if that's the best image to look at, but the Monte Carlo scheme basically is not restricted by dynamics. Basically, I pick an atom at random, and I move it could be a fairly large distance, say like 3 angstroms. And if that energy is lower for that new position, that that new configuration is accepted. Basically, there's a Boltzmann factor in there which determines whether these configurations are accepted or not. So it's a fast way to determine local composition without the restrictions of molecular dynamics where you have to solve F equals ma to move an atom.
Right, so actually allowing for these
Yeah,
kind of
yeah,
changes.
yeah. So there's no restriction to a lattice here. These atoms can move wherever they want. Yeah.
Question in the back?
So for your systems that consist of, say, 15,000 atoms,
Yes.
what kind of resources, software
Mm-hmm.
do you use, and how long do they take on those?
Yeah, so we're using this highly optimized LAMPS code, which was written at Sandia National Lab. It scales rather well to large numbers of processors. Even for 15,000, that's kind of a small molecular dynamics calculation. If you ask a real MD person, they'd say, oh, it's not interesting unless you're doing 1 million or 100,000 or more. So this we can run on, say, 16 cores, 32 cores. And remember, we're doing both Monte Carlo and molecular dynamics. These mean square displacements would take, say, a matter of days. The Monte Carlo also on the order of a day or two, so not extremely expensive. I mean, we have, of course, different temperatures and different grain boundary structures, and there's multiple steps associated with these processes. So you put all that together, and Xiang-Ho could probably redo all the calculations now in 2 weeks, but the first time you do it, things don't work out. So it takes about 5 times longer than that, I'd say.
Thank you for the presentation. So my first question is that how the grain boundary influence the share modules?
Oh, a good question. I don't know. That's something that more than one person has asked me. So I'm thinking about a way that we could calculate that. I mean, it's possible that the system is softer in the region of the grain boundary.
Is that the reason why the dendrite matrix go there? It's my
Maybe. I personally don't think that's it. I think there's something. I think there's an electrochemical reason, or a composition difference region, or a microstructural feature. Maybe there's some porosity there we don't know about that exists at that grain boundary junction. So if this is lithium metal, and I take my LLZO, imagine this is a grain boundary. If I put it up like that, maybe there's some void space here that results in the nucleation of those dendrites. Yeah, sure.
second question about the grain boundary connectivity. What are the general way to improve the grain boundary connectivity?
Yeah, I think you could of course just anneal the system at higher temperatures, and presumably if you had some disorder, maybe dislocations at the grain boundaries, those would anneal out, and you would have so in that case, one could expect that if you heat the system for a long enough period of time at a high enough temperature without melting the thing, in that case I would expect you would come rather close to achieving grain boundaries that looked like these nice compact coincident site boundaries that I have here. So there might be other chemical routes to improving grain boundary connectivity. I don't know enough about them, but doping of grain boundaries, people try to do that sometimes. Sure.
About the wet polishing and heating treatment.
Yeah.
So, question about heat treatment.
Yeah.
Do you need to heat it under the protection gas atmosphere or just in the air?
Yeah. So I'll tell you what I know about these experiments. All of the polishing in this case is done outside of a glove box, and then after that polishing is done, they stuff it in the glove box right away. So one reason why I think that this wet polishing works better is that it probably protects probably prevents some reaction with the atmosphere due to the presence of this liquid phase. Of course, that liquid phase is doing other things like maybe protonating the LLZO. But yeah, this polishing is all done outside of the glove box, and then the heating is done inside a glove box. Say again?
Like any microscopical studies on the grain boundary?
Well, so I have this one TEM image from Oak Ridge, which I don't think has been published. Where did that go? So so I mentioned that I would like to have some more data on grain boundaries. So to specify a grain boundary, you need 5 degrees of freedom, and then you, in principle, also need some microscopic translations in the grain boundary plane, which we can calculate. But as far as I know, this is the only thing that I'm aware of that has the sort of atomic resolution that one could build an atomic scale model out of it. I don't even know if this has been published.
Okay. A normal question?
I have one tiny
Yeah, okay,
question.
one more question.
One tiny question. What is the shear modulus of LTPS? You said something.
Oh, it's actually it's maybe like 7.9 or something.
Is that all?
It's right on the, it's just below what you'd want it to be based on the Monroe-Newman criterion. Based on the calculations that I saw, yeah.
It's not a great material anyway because it reduces, but
Sure.
that's sort of classic values for sulfides?
So I don't know how generalizable that is for other sulfides. I mean, I don't actually know if again, the number I'm reporting is a calculation, and those calculations got, their values were comparable, but I think, I can't remember if they were higher or lower than what we got for LLZO. But I think the conclusion is that it's marginal, according to the Monroe-Newman criterion, is true, with the caveat that I haven't actually seen an actual an experimental measurement.
And the real problem is, postdoc Shell was just saying, it's really the green boundary issue anyway, so.
Right. Well, I mean, sure, it's, like I point out at the beginning, you check one box and you go through these things and you find other interesting, unexpected problems arise. So I think that's kind of fun. Maybe other people would get frustrated by that, but we're learning some new things.
Great.
Okay, one last question here.
So we calculate the molecular
Yeah,
dynamics on
yeah,
the grain boundaries.
yeah.
Today what you show is the trajectory of
Yes.
the lithium.
Yes.
So does the chlorine or oxide, oxygen, how does they move?
They don't really move much at all. So I haven't shown them here. They basically just stay at one point in space.
So even there is some angle between I believe at the boundaries,
Yeah.
there's some instability in terms of from
Oh, okay. Well, I mean, so I would guess that maybe the mobility of the non-lithium components is probably a little bit higher at the grain boundary. I actually don't know. It could be lower at the grain boundary. We really haven't looked at it because when we've looked at the other non-lithium species in other contexts, they just kind of sit where they are and don't do much. So we haven't actually checked, but I'd be surprised if they were doing anything different than what we expect them to.
Okay, let's wrap up. Let's
Okay.
thank our speaker.
Thank you.